Good morning. Well, it might not be morning when you're watching this, but this is Mr. Hunter, and this is your Electrostatics Notes Part 3. So, last time I had you here, we were talking about the difference between series and parallel circuits, as well as finishing up talking about voltage. So I just want to quickly refresh your memory about that. A series circuit is a circuit where electrons can only go in one path. So that means that electrons can go out of the positive terminal from the battery through whatever parts are in the circuit and then back into the battery, like this picture that you see below, where I have a battery going into a lamp, going into a resistor, going across a switch, and back into the negative part of the battery. Now, remember, just as a refresher, when the switch is open, there's no potential difference. We have broken the path, and there's not a complete path from the positive to negative, because remember, we need a potential difference in order for electrons to flow. So, in a series circuit, since electrons can only take one path, they can only go as fast as the electron in front of them. Think about it like if you're in a one-lane road, and you can't really go as fast as the car in front of you because you can't pass them. There's like no way to pass them, so you can only go as fast as the car in front of you, and it's the same with electrons. Electrons, one, take the path of least resistance. They still take paths of higher resistance, remember, but they take the path of the least resistance. More of the electrons will flow through the path with that's easier to take. Additionally, they can't move faster than each other. That's why the total current, and someone pointed out I wrote an additional I, that's what it was, that I had wrote this wrong, so I apologize. So it's I total equals I1 equals I2 equals I3. And I was so rushed for time, I couldn't really tell you what the I1s, I2s, and I3s were. So the I1 would be like, for example, the current through this lamp. And I2 would be the current through this resistor. And I3 would be the current through this switch. So because electrons can only take one path, and they can only go as fast as the electron in front of them, they all have the same current in a series circuit because they can all take one path. This additionally is why we measure current in series. So when I have a battery, and like let's say I want to measure a lamp, and then I put the ammeter in series, and that's why we put the ammeter in series, so that the current doesn't change when I put the ammeter in series. So ammeter gets plugged in series, so we don't change the current by measuring it. So we don't change the current by measuring it, which means, let's see, so the ammeter has, let's see, would an ammeter have super high or super low resistance? It's a good question. Hopefully you're thinking about it, and actually I want you to say out loud, what do you think it would have? Would it have a super high or super low resistance? Okay, hopefully you said it would have a super low resistance, because think about it. Resistance changes the current, because resistance doesn't like the flow of electrons, and a current is how fast the electrons are flowing. So an ammeter would have really low resistance in it. So really, really low resistance, or I like to say in class, resistance. Okay, so now the total voltage equals the voltage, the addition of all the voltages across those parts. Why? Because think about it this way. Like, you have a certain amount of energy, right? Let's pretend you're running a track and field race. You have a certain amount of energy, and you run over the first hurdle. Well, you're not going to have as much energy as you did before, because you use some of it getting over that first hurdle. And then you run and you get across the second hurdle, which is like this second resistor. Well, you've used some of that energy or some of that potential difference to get across that second hurdle, and so on and so forth for the rest of the hurdles. And if you add up all that energy you used, it would equal the total energy, like conservation of energy, but this time with voltage. So in a series circuit, V1 is the voltage across the first part in the circuit, which in this case is our lamp. And then V2, or actually would be a switch technically because of the way I drew the circuit, but oh well. V2 would be the voltage across the resistor, and we can get that two ways. We can either do V equals IR, or we can measure it with a voltmeter. And then resistance is the same thing. Resistance in a circuit is just the total resistance in a series circuit is all the resistance added up. Now, the equations change slightly for a parallel circuit. For a parallel circuit, it kind of changes. Now, remember, a parallel circuit is one which electrons can take multiple paths. So as you see here, the electrons come out of the positive, and they can either split and go through R1 or split and go through R2. And remember from what I said, most of the electrons will take the path of least resistance. So like if R1 is 1 ohm and R2 is 100 ohms, a lot of the electrons are going to go through R1. You're still going to get some electrons to go through R2 because it's connected and it's in the path, but there will be a lot more current through R1. Remember how I equated it to students. Students take the path of least resistance. They take the easiest job to get it, like easiest amount of work to get the job done. Most students do. Some students go above and beyond and do what they should do, which is work hard so that they can have the best understanding and be really, really good and get A's. But most average student just cares about barely understanding anything. It's kind of sad. So in a parallel circuit, the total current equals the current across each part. And think about this. This makes sense because the electrons are taking different paths. Because they're taking different paths, the current is going to be totaled up. So you got to add them all together. The voltage, however, that equals the same in each part. And here's why. It's like the things are directly connected to the battery. For example, since it's all metal connectors, right? Technically, this guy, whoops, I shouldn't use green because that's what I do my circuit in. This guy and this connection right here are connected directly to the battery. Because look, this guy is connected to this guy is connected to this. It's all metal. And the same thing here. This resistor is connected to this resistor, and this end is connected to that end. So it's all like they're connected directly to the battery. That's why the voltage is the same in a parallel circuit, because it's like they're all connected directly to the battery. And it's the same reason why we connect a voltmeter in parallel, because we don't want to change the voltage, because the voltage is the same in the parallel circuit. So that's why we measure voltage in parallel, so that we don't change the voltage. So hopefully you write that down, because I am running out of time. So I'll just put measure voltage in parallel, and we do that because we don't want to change the voltage. And would the voltage have a really, really high or a really, really low resistance? Now think about it. We don't want a lot of electrons flowing through it. So a voltmeter is going to have a really, really high resistance. Why? Because we don't want to change the voltage, and we don't want a lot of electrons to go through the voltmeter, because that would significantly change our current. So in a nutshell, that's why we measure current in series. It's why we measure voltage in parallel. And then lastly, the resistance equation is a little different. The real equation that you'll see in your reference table is 1 over the total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, which means when you're solving it, you have to put 1 over R1, and then you have to add it to 1 over R2, and then have to add it to do 1 over R3, and then take the inverse reciprocal, because you're solving for RT, which we're not going to do here. We're actually going to do that in class. And with my last minute of time, I'm just going to quickly go over what electricity is, but you know by now. So electricity is basically the flow of electrons. Right? And so as it says here, electrons flow from negative or from positive to negative in a closed loop. And in order for electrons to flow, the path must be complete. This means that there must be a complete path from the terminal, from the positive terminal to the negative terminal. I guess that was information you're supposed to fill in, but it doesn't have a line. Okay, so this is the conclusion of electrodynamics. There is one more thing I have to show you, which I might have to make a new capture sheet. We're just going to have to add to this on magnetic fields and electric fields and how they interact with each other. Okay, I will be collecting this in class, or creating this in class. Goodbye.